All right, so this is our section 15.8, 15.9 supplemental video 2. So we've learned now how to convert from cylindrical to rectangular, or rectangular to cylindrical. Really, it's just polar with z added in there. And then we learned spherical and how to what the coordinates are for spherical coordinates. We just haven't practiced any. So let's go ahead and practice a couple of things we're using spherical or getting to or going from spherical coordinates. So the first one says, convert the point 1 square root of 3, 2 square root of 3 from rectangular to spherical. So until you really get the hang of this, and obviously I expect that you're probably going to be using the formulas for now, it still helps to kind of write, okay, what are we doing here? We're actually going from x, y, z, because that's rectangular, to spherical, which is rho theta. I'm sorry, rho theta. I wrote that wrong. Come on, erase. There we go. Rho theta phi. So we need to find those things. We're given x, y, and z. We need to find rho, theta, and phi. So you can do this in whatever order is easiest for you. Personally, I usually just kind of go right along the order there. I'm going to find rho, which again, rho is x squared plus y squared plus z squared. Well, that's rho squared. So let's go ahead and put that in there. So we've got rho squared is x squared plus y squared plus z squared. And then we can solve for rho. And again, we're going to go with the principal rho value, which is going to be the positive of the square root. So that's going to be 1 plus 3, and then 2 root 3 squared is 4 times 3 is 12. So we're going to get 15, 16. That works out quite nicely because then rho is going to be 4. So the radius of the sphere from the origin is going to be 4. Okay, so we're also going to need to find theta. Got our rho, let's find theta. Theta can be done by tangent of theta equals y over x. It's going to be the same thing as it was in polar because we're using y's and x's. So that means that tangent theta here is going to be square root of 3 over 1, which is square root of 3. And theta is going to be at, let's see, what is that? Pi thirds for square root of 3. And third quadrant 4 pi thirds. Okay, so it's going to be one of those two. Now, looking at our original coordinate, everything's positive. So we're basically in the positive first octant, which means it's going to be the pi thirds. So theta here is going to equal pi thirds. And then we need to find phi. And there's multiple ways you could go about finding phi. I'm just going to go with one of them, which was that cosine of phi equals z over rho. So let's see, that means that cosine of phi is going to be z was 2 square root of 3 over rho, which is 4, which simplifies to square root of 3 over 2. That makes things a lot nicer. So where is cosine going to give us root 3 over 2? Specifically, it doesn't have to be for phi, because remember, phi is the angle of Bloom. But we're going to go with the positive value of this, or the first octant value of this, or the first 2 octants. I need to do one more explanation after this. So let's see. Root 3 over 2 for cosine is going to be at pi sixth, or, nope, 5 pi 6 would be negative. So it would be at pi 6. It would also be at 11 pi 6. Here's the thing. An angle of Bloom can only go from 0 to pi. Think about this. I'll write the coordinate up there in a second. The angle of Bloom is the angle which is made from the positive z-axis. And the idea is that you have to remember that this angle opens up in every direction. So it's going to open up this way. It's also going to open up this way at the same time, and then out that way in the back, and then this way out in the front. The angle of Bloom basically opens up the flower 3-dimensionally all the way around. So an angle can only open as far as pi. Once it passes the negative z-axis on the bottom, then it's no longer opening. It's actually starting to close again. So an angle of Bloom, phi, can only go from 0 to pi. That's as far as it can go. So in this case, it's pi sixth. So it's only opening up pi sixth. So in our particular case here, we can actually do a quick sketch just to see what this looks like. Let's see, it's got an angle of pi thirds, which is going to come out, 2/3 of the way that way, basically. So somewhere around there. It's got an angle of Bloom of pi six, which is really not that far, maybe right here. And then it's got a rho of, we'll just say that that's 4. But that's basically what it would look like. So there's your theta, there's your phi, there's theta, and then your rho value is the solid line. So that's rho. So your point would be someplace like that. So our actual coordinate here is rho, theta, phi. That is a spherical coordinate for 1 square root of 3, 2 square root of 3. All right, let's move along. I won't do a sketch like that for every single one of these, but I just wanted to show you the general idea. All right, now we want to convert the point 1 pi 6 square root of 3 from cylindrical to spherical. Okay, so now we're going from r theta z to spherical, which is rho theta phi. Okay, and the nice thing is theta is theta. Either way, it's the exact same thing. So we've got theta, that's pi 6. We're kind of done with that part. We do need to find rho, we need to find phi. Well, we can find rho, and typically this is, to me, it's the easiest one to start with, because rho squared, we know going from Cartesian, it's x squared plus y squared equals z squared. But remember, x squared plus y squared is r squared. So it's r squared plus z squared. And we have those pieces. So rho squared is going to be r squared, which is 1 squared, plus z squared, which is square root of 3 squared. So we end up with 1 plus 3 is 4. So rho is going to equal 2. And then once again, we have plenty of formulas that we could use to find phi. I'm just going to go back to the cosine one. For whatever reason, it's just the one that I remember easiest, and that's z over rho. Z over rho. So cosine of phi is z, which is root 3, over rho, which is 2. And we just kind of did this one in the previous problem. That's going to give us pi sixth. And we already have theta. So our spherical coordinate becomes 2 pi sixth pi sixth. Okay, and like I said, I do not expect you to be as quick as I am at this right now because I've done this for a long time, but you'll get used to it after you use these enough. Okay, let's do another one. This time we want to convert the point, which is 8 pi 6 pi halves, from spherical back to cylindrical. So not necessarily to rectangular, back to cylindrical. So this is already in spherical. So we are going from rho theta phi to cylindrical, which is r theta z. So again, theta is theta. That makes it nice. Okay, so we are going to need to find r, and we're going to need to find z. So in this case, it doesn't really matter. I'm just going to do the z part first. So again, I'm going to start off with the fact that cosine of phi equals z over rho. But I need to find z, so let's multiply both sides by rho. So do I have rho? Yes, because that's what they gave us. That's 8. I have phi, which is pi halves. So cosine of pi halves equals z. Of course, cosine of pi halves is 0, so that makes it quite nice that z here is 0. And then we need to find r. And we can find r because r is rho squared minus z squared. And where did that come from? Well, rho squared equals r squared plus z squared. So I just subtracted z squared on both sides. So r squared is going to equal rho squared, which is 8 squared, minus z squared, which we just found was 0. Really nice. So r squared equals 64, or r equals 8. So now we've got r, theta, and z, because theta was given to us in the original. So it's 8 pi 6, 0, which is actually something which is on the xy plane. And if you think about that, that should make sense. Look at your angle of Bloom. Look at what phi was. Phi was pi halves, which is from the positive z-axis down to the xy plane. Okay, it's a 90-degree angle from the z-axis, so it puts you in the xy plane. So it makes sense. All right. Equations in spherical coordinates. So let's look at a couple of equations. These are actually from the book. I did not type them up. So let's see how this would look. Let's do the equation z equals r squared, and we want to convert that into rectangular so that maybe it'll make a little bit more sense. So we're going to say convert to rectangular. Well, to convert something into rectangular, you basically need to have x, y, and z only. Right now we've got r squared, but hopefully we remember that r squared is x squared plus y squared. So we get the equation z equals x squared plus y squared. And if you happen to remember what that looks like, that's great. This one will be a, wow, I'm just totally drawing on a blank on this. Paraboloid. Wow, don't know why I was drawing a blank on that. So there you go. Let's see. Let's do, oh, not paraboloid. Wow, I am really just drawing a blank right now. Have those moments every while. This is an elliptic paraboloid, right? Parabola is in two directions, and an ellipse or circle in this case on the top one. So it's an elliptic paraboloid. I think I spelled that right. Yeah, good enough. All right, so now let's do r squared plus z squared equals 25. And let's go ahead and put that, yeah, let's put that also into rectangular. Well, r squared is x squared plus y squared. So we get x squared plus y squared plus z squared equals 25. And hopefully you can clearly see that that is a sphere. Oops. Come on, there we go. Sphere with a radius of 5, and I am not going to even try to do the traces specifically. To me, it's just easier just to draw a circle and then kind of three-dimensionally fill in what it would look like, something like this. I think that's a pretty good sphere overall. It's not bad with a radius of 5. Sphere, or R, equals 5. All right, let's try a couple more. That's why there's some more pages. You won't need all these pages. We're only going to do 2 more relatively quickly. So we're going to convert to cylindrical and spherical. So I'm going to give you something which is in rectangular to start. So we're going to take the equation, and we kind of already did this before, but we're going to take the equation z equals x squared plus y squared, and we're going to put it into cylindrical. Okay, not too difficult to do. Remember, cylindrical is r theta z. Well, let's see. Z is r squared. Everything in that equation is now in terms of z's and r's. This is taking equations and creating equations in cylindrical now. So z equals r squared, we're done. But now let's say we wanted to take that and put it into spherical. Let's go with red. All right, well, if I want to change that into spherical, that's going to be something we need in terms of only rho, theta, and phi. So we've got to put z equals r squared or z equals x squared plus y squared into terms of only rho, theta, and phi. And typically we try to solve for rho if possible, but we'll see if it's possible here. Okay, well, I'm going to go from cylindrical. I think it's probably easier in this case. That's probably easier to go from rectangular, although it doesn't matter. Z is going to be the same thing as rho cosine phi, and that comes from one of our equations, our transformation equations. So rho is z equals rho cosine phi. X, it's rho sine phi cosine phi, and again I kind of transform that from rho sine phi cosine theta. Remember that rho sine phi is r times cosine theta. That's what x is in spherical, and that's got to be squared because it's x squared here. And then y is rho sine phi, which is r, times sine theta. So that's kind of your polar equivalent. So let's see, we're going to get rho cosine phi equals, squaring everything over here on the left-hand side, I'm going to get rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta. Okay, the nice thing is I can factor a rho squared sine squared phi out of each term. And I'm sure you can probably already see what's going to happen. I'm going to get rho squared sine squared phi times cosine squared theta plus sine squared theta, which of course is 1. So we're going to get rho cosine phi equals rho squared sine squared phi. I can divide both sides by cosine phi, and we get rho. I probably don't want to do that actually. I want to divide both sides by sine squared, and I'll explain that in a second. So we're going to get rho cosine phi over sine squared phi equals rho squared. Now I can divide a rho out of each side. And yes, we can do that. We're not losing anything here because of the fact that rho is just rho. It's the distance from the pole out to the edge of the sphere. So we can actually do that in this case. So we're going to get rho equals, let's see, cosine phi over sine of phi is cotangent of phi. But that's still going to leave me with a sine of phi in the denominator. So I would get cotangent phi, and then I would technically still have times 1 over sine phi, but that's the same as cosecant phi. So that is probably the most simplified equation in spherical. All right, a little bit more work obviously to get to the spherical, but not too bad overall if you know your conversions and the algebra. All right, that's plenty enough. That's your conversions in spherical and cylindrical coordinates.